Hello, this is Professor Watson. For every class in this section, I'm trying to do a pre-recap where I go back and talk a little bit about things that happened during class and some of the common questions that came up. This is hopefully something that will both serve to kind of consolidate and synthesize the memory of what happened during this class, but also to introduce the next class and to provide some sort of evergreen ideas that are things that I say very often. So in today's class, we were just setting up and recapping the basics of what's going to go down in machine learning. We talked a little bit about the introductory machine learning concepts that I brought up in some of the prior videos, where this is kind of a synthesis of math, computer science, engineering, and also particular culture and history of the mathematics of machine learning. I also talked about how classes are going to play it out, how we'll have a more code and engineering focused pre-class work for over the weekend, so that when we start on Tuesdays, we'll tend to be working on a model or a pipeline that has produced predictions on a set of data. Then we'll crack open that black box. And so that most Thursdays, you'll have a math focused pre-class work where we'll zoom in on specific equations and we'll really unpack how it works, what predictions it's making, what it means for our model. We might occasionally have classes pre-assignment where we talk about a specific assignment that's coming up. Our first assignment that's coming up is the location-based assignment. This is a super fun assignment where you go out and you take a bunch of pictures of a landmark in the city that you're in, and then you use PCA to try to identify some of the kind of eigen pictures, so some of the factors that stay constant, even when your camera is moving around, even when the colors outside are changing. As stuff changes in the picture, what is the stuff that remains constant? And then how can you generate pictures using those eigen pictures? So it's a super fun assignment. I really enjoy it. We'll spend some time on that in one of our pre-assignments. Uh, the next thing that we did is just talk about mind maps. Students provide a lot of cool mind maps. I'm going to grab a couple examples here from some of the groups. Here are a couple examples of mind maps. A lot of students split algorithms into kind of supervised, unsupervised, and maybe reinforcement learning or some self-supervised learning off to the side. They talked about classification and regression. They built this rich tree out, starting from very high level concepts like algorithms and then building out these side branches. That's very much what that first chapter of the book describes. So those are interesting. I also liked how students tried to integrate some of these different ideas into their group four. This is particularly good. Integrate some of these different ideas like discriminative and generative models. We talked a little bit in the class about how there are different goals in machine learning. Sometimes you want to generate samples from a distribution. So you want to kind of give people examples of the sort of thing that this model has learned about. Other times you want to assign category labels, like you want to classify something as a dog and cat, for instance. And those are fundamentally different statistical methods that you want to approach in different ways with different kinds of probability distributions. Maybe one's more conditional probability, the other's more joint probability. So these are great ways to start thinking about this really complex topic and start integrating these new ideas. So I really enjoyed that. The next thing we did is just a bunch of class logistics. One of the things that I think is great for this class is I'm actually trying to leverage as much as possible students' contributions to the class. So I'm having students have a common note document that they all can contribute to. I made sure everyone had access to the previous GitHub repository of last year's code in case they want to look ahead or see what's coming. The other major thing is everybody should be in the Slack channel. If you can talk to me there, then that's the best way to get in contact with me. The last thing I did, and I really, really like to stress this point because this is very important to me, is talk about class culture. So one of the major elements that I think is always true, and in most classes, this is especially true in technical or mathematical classes, is that students are often coming from a background where there is a lot of anxiety in learning. And that anxiety typically comes from a pattern of authority and power that takes place in a classroom, right? The teacher is an authority figure and they're asking you to do stuff and they're, using their power to try to induce you to do stuff. Hopefully they are a good leader, right? And that they are asking you to do things that are just and that are in your best interest and that are helpful. They're using their greater wisdom to foresee what you need to know in class. However, sometimes that's not the case. Sometimes they are being, mildly abusive. Hopefully that doesn't happen very much. Other times, though, they are just implementing a larger bureaucracy that they don't think is a good idea. And it's often very clear when that's the case, and the teacher often has some kind of negative emotional energy, and that ends up slowing up. One of the cases that I think this comes up a lot in is especially in mathematical and technical classes, where there is a culture among highly technical and highly mathematical folks um, where, these are very good paying jobs. Finance and technology are some of the highest paying sectors and they require a lot of math. And so these jobs are sort of defended, and there is sort of a group of kind of a guild that wants to keep folks out. And so the teaching methods they use substandard teaching methods, and they tend to police the knowledge a little bit. They tend to filter a little bit. And they often do this in a very subtle and passive way where they simply, ask a difficult question and expect you to respond to it as quickly as possible. And rather than thinking it through. And that tends to make people respond wrong. And then when they notice that people have responded wrong, they exclude them, right? This is very poor teaching. In fact, it's almost the opposite of teaching because you're just kind of giving tests. You're just kind of filtering for people who already have the background, already know the knowledge. And usually what you find is people who know that stuff come from privileged backgrounds. They have money, they have more groups that are part of the dominant culture. They have parents who are mathematicians, right? They have every advantage, right? And that's why they know. That's why they're a little bit better. And so you tend to get this selection bias for folks who already know the mathematics in the area because of this dynamic that gets set up. I think that's very poor teaching practice. I think that excludes a lot of people who would be perfectly good at math unnecessarily. I think it's a little bit outrageous. It reminds me a little bit of a time kind of around the invention of the printing press, where reading was the sort of defended art, right? And it's kind of like these scribes and scholars are not teaching people to read. They're not teaching people mathematics because you can make a lot of money with using mathematics. I don't think that's a particularly good or defensible or just way to go about things. So I try not to do that. But I know that a lot of students come into my class having been through this long filter, having been kind of harassed over and over again about their technical knowledge, having been told over and over again, prove yourself, show me that you know this mathematical knowledge. And that causes a lot of, I think, very understandable anxiety in these situations where they are now suddenly asked to perform this question. And so I try not to do that. Try to give people time to think about things, because mathematics is a very slow discipline and it's a very progressive discipline where you're building up very slowly over time. It requires an intricate understanding, a lot of observation. Asking a bunch of really quick questions will actually tend to filter people much more on the basis of luck and much more on the basis of speed than it will on actual underlying knowledge, especially if you're asking very simple, like yes, no questions. If you're asking yes, no questions, and it's one of the things when studying machine learning class, people will do very well. And it's not because people who do very well are much more likely to have just gotten very lucky than to actually know anything about the discipline. And this ends up in problems later when you're trying to teach them stuff. You assume that they know all this stuff that you were really just filtering them out on their ability to answer very quickly. And the people who answered more slowly might actually, have actually some of the subtle caveats that they were thinking through, but they weren't able to answer quickly, and they weren't able to, they weren't willing to commit really strongly to one side of the answer. So you end up filtering out a lot of people who know stuff pretty well and keeping a lot of people who are just fast and got lucky. So I try not to do that. And I really want to say to everybody who is trying to learn machine learning, you can do this. It's a slow process. It's like learning a language. There's a lot of skill-based practice in engineering. You'll get things wrong, but that's totally normal. That's not actually evidence that you're excluded from it. In fact, one of the things that I think is actually kind of painful for me to watch is often very, very gifted students, when they encounter something like machine learning, which is a genuinely hard discipline that requires a lot of practice, a lot of skill building over time. They are so unused to learning in a domain where things are not easy, to learning stuff where they'll have to practice and they'll have to come back and do things over and over again, that they meet this, they're used to being that student who's the fastest. They're used to being that student who's lucky. And when they encounter something that's just too complex for you to give, glib, quick answers to, and when their ability to memorize things really quickly and their strong basis of background knowledge and their good, fluid intelligence, well, that's not enough anymore because we're doing this genuinely difficult thing that requires practice, skill, and time. Suddenly they feel like it's not for them. And that's really sad because they would be some of the best at it were they to stick it out. Were they to understand that, no, it's just going to take, you're going to have to be wrong a lot. You're going to have to get a lot of negative feedback in this area, much more than you're used to because you're used to not getting any. And so I always like to start out my class by saying culturally, hey, you can do this. You can make your way through this. It will be hard. There will be a lot of practice, right? Things won't snap into place immediately. If you read a textbook, you'll probably have to reread it. One of the things I said to students who stuck around after class is, one of my professors told me, hey, if you really want to understand a page of mathematical equations, you got to read that page for an hour. It's about an hour to read a page of mathematical equations. That's a reasonable amount of time to spend on it. If anybody is trying to, you know, rush through it, get through that page faster than an hour, hey, you're not going to do it. You need to label every single variable. You need to think about what the different patterns are, right? If something is divided by something, that means it's scaling that top part down, right? That's, that's an intuition that you would have if you sat there for an hour, right? But if you don't sit there for an hour and have intuition, you won't really understand. And, that doesn't mean that every time, you need to read mathematics, you need to spend an hour. It depends on the context, right? Sometimes you're just trying to learn the vocabulary. Sometimes you're just trying to get exposure to it so that you can see the notation. That's your set. That's all that. But if you really want to understand it, it's a long and arduous process. And I really want people who want to do that long and arduous process. The rewards are great, not just in terms of you'll get the highest paid jobs, but also in terms of, I really think the mathematics of machine learning are so beautiful and so applicable to the real world. You start to see these things all the time. And you start to use the language of machine learning to explain your ordinary life. And it changes the way you look at things as simple as, what a picture is, right? You see the world in a fundamentally different way, in a way that's really powerful and beautiful, and interesting and fascinating. And I really love it. And it took me a long time to see the world that way. And I was not, I'm a biologist. And so I did not start out with the mathematical background. It took me a long time to build those intuitions. I did not assume that I was going to have them right away because my background was much more in life sciences. And so I got there eventually, and I was really glad I did. And I hope that students coming in this class do something similar. It's going to be hard. You're going to miss a lot. It's not going to be easy for you right away. That's okay. That's an ordinary expectation. I do not expect you to be brilliant right out of the box. I expect you to work hard, to think about things deeply, and to please just go easy on yourself. I want you to be brave. I want you to be able to ask questions of me. I want you to feel safe and okay that you can do it. And I want you to hold yourself to a standard of learning that all you have to do is understand this topic and get a little bit better at it and practice the code and practice the equations and wait, have great patience. The end of this trajectory, if you really want to be working in AI and machine learning, it's a 20-year project, 10 to 20-year project. Right? You want to go to graduate school, you want to understand stuff. You want to make contributions. You want to be the one who creates the next Dolly or something like that. It's a 10 to 20-year practice. And that's okay. If you're willing to take that time, you'll get there eventually. And it's worth it. It's also okay to just spend and just understand a little better and see the world a little differently and learn stuff. So think of yourself as walking this very long path. And as long as you're getting better, you're doing the right thing. You can get there eventually. Some people get there a little faster than others, but nobody gets there fast. And so, don't beat yourself up for not being able to run quite as fast as another student in class or quite as fast as you wish you could. Just say, hey, I'm going to do my best. I'm going to show up every day. I'm going to work hard, and the next day I'll do better. That's all you need to do to all better. All right. Thanks. One last thing. For next class, I'm going to have people do, to that end, I'm going to have people do what was an assignment in a previous class. So here it is. I gave a couple of data sets. One is a numerical data set about testing various computer processors to see how well Moore's law is holding up. Moore's law is this idea that the number of transistors on a chip doubles every 8 months. So there should be this exponential relationship. I would like you to do some regression to see if there is that exponential relationship. And then there's also a pictorial data set of the MNIST digits. I'd like you to pull those in and try to to do a logistic regression to classify a pair of them. I've linked some good resources to help you with these two problems. And what I'm really looking for here is just, I'm checking people's ability to do coding. It's okay to ask questions. It's okay to ask for help on the Slack channel. I expect everyone to be able to do this. This is pretty similar to what we've done in your previous statistics classes. It's just using some of the new packages like scikit-learn that you may not be entirely familiar. For right now, it's okay if you do these as black boxes. We're going to crack them open in the next class that follows these and start to look more in depth at these models and really understand what's going on inside. All right. And with that, that's it. I will see you back here on Thursday.